Okay, sorry. All right. So is my slides visible to everyone?
Yes, sir.
Okay. So what we said is we have started looking at these rectangular uh, solid geometry and unsteady state heat transfer. Here also we have considered all three direction of the heat transfer, isn't it? So the final expression which we have obtained in the last class was this 1 by alpha dou t by dou t equals to del square t plus psi v by k. So this is the generalized expression. Again, this equation can be simplified depending on what type of situation we are looking at. For instance, if we are having a one dimensional heat transfer, in that case we will only have this first term uh, dou square t by dou x square. And if there is no generation term, then the psi v by k will also be absent, isn't it? So this is the standard second law, second Fourier second law of heat conduction. 1 by alpha dou t by dou t equals to uh, dou square t by dou x square, isn't it? This is the similar to if you look at the unsteady state diffusion equation, isn't it? If you remember, I don't know whether you remember or not, but this, a similar equation you get it for the mass transfer also, where you get 1 by d dou c by dou t, that is equals to dou square c by dou x square, isn't it? So if this generation term is not there, then we directly get generation, and the accumulation term is not there, then we get only this del square t equals to 0. So this is the standard Laplace equation. Okay. All right. So whenever this generation and accumulation term is absent, we just start with this Laplace equation and simplify it and solve it, isn't it? All right. So then this idea of multi-dimensional heat transfer and the unsteady state condition, this we have extended for the cylindrical geometry, and in a cylindrical geometry also we have obtained a generalized equation like this. So in this case we have obtained 1 by alpha dou t by dou t equals to dou square t by dou r square plus 1 by r dou t by dou r plus dou square t by dou z square plus psi v by k. Okay, so this is the generalized expression. Again, in all these derivations, we have assumed that the thermal conductivity, density, and specific heat, these are constant and these are not dependent on temperature. That is what we have assumed. Okay. So one more thing to note down here is in a flat geometry, we are looking at all three directions x, y, z. In a cylindrical geometry, we are looking at only two direction r and z. Whereas when we look at a spherical geometry, in a spherical geometry, we only look at one direction, that is r. Okay, so in a spherical geometry, again we get a generalized expression as shown here: 1 by alpha dou t by dou t equals to dou square t by dou r square plus 2 by r dou t by dou r plus psi v by k. Okay, this is a generalized expression with the assumption that thermal conductivity, specific heat, and density are independent of temperature. Okay, so is it clear? Up till now we have looked at in the last class. Is it clear to everyone? Hello.
Yes, sir.
Okay, so now let's extend this. Okay, again this concept of unsteady state heat transfer we have looked in the context of this lumped heat capacity method. So what we said is if you wanted to find out the time required for body to reach to a particular temperature in an unsteady state heat transfer, if we assume a body as a lumped parameter, that means the conduction resistance is relatively negligible compared to the convective resistance. In that case, the complete body we can consider as a one single lump with a same heat capacity, and in that case the balance equations becomes further simplified. Okay, so one simple example we have taken here: we have considered a solid metal ball, and that metal ball we have put it into a higher temperature fluid suddenly, and then we are looking at how the temperature of this ball is going to change. Of course there will be a temperature gradient between the surface of this ball and the center of this ball, but since this being a metal ball, thermal conductivity of this metal is going to be much higher compared to this liquid, and therefore the conduction resistance is going to be lower. Conduction resistance is going to be lower compared to the convective resistance. Convective resistance for the heat transfer between the fluid and the solid. Okay, so in such cases we can assume that this this entire ball is a single unit, and the heat capacity of this entire ball we are considering a single unit, and we are assuming that the internal resistance of this ball is negligible. So to have this assumption, we first need to calculate the Biot number. If Biot number is less than 0.1, then and then only you can assume that the internal resistance of this metal ball is negligible. Okay, and then only you can apply this entire analysis. So first, while applying this particular thing, particular analysis, you first need to calculate the Biot number. If that Biot number is less than 0.1, then and then only you can go ahead with this. Okay. So what we have done here is the rate of change of heat energy will be in that case equals to just the heat transferred by convection. Okay. Because there is a conduction is negligible. Conduction is negligible. So whatever the temperature change of this entire body is taking place, that is nothing but the rate of change of internal energy that we can equate to the how much heat is transferred by this fluid to this metal ball via convection. So that is what we have equated. So this convection term is equated to the rate of change of energy. So that is nothing but the accumulation term. If we rearrange everything, what we get is Tt minus T infinity divided by T naught minus T infinity is given as exponential of minus HA by rho CPV T. Okay. So again, this HAT divided by rho CPV we can rearrange, and we can represent this in terms of two dimensionless number, and these two dimensionless numbers are Biot number and Fourier number. So Biot number is calculated by this equation Hs by K, where H is nothing but the heat transfer coefficient, S is the characteristic dimension, and K is the thermal conductivity. And this Biot number has to be less than 0.1 in order to apply this equation. Okay. So basically the Biot number compares the magnitude of surface convection and the internal conduction resistance, and you can apply this equation only if the internal resistance is negligible. So internal resistance negligible, that means what? The conduction term which is there in the denominator should be very high, isn't it? So that means Biot number should be as low as possible. Remember, this numerator gives me the convection the magnitude of convection, whereas this denominator gives me the magnitude of conduction. So if I am saying the conduction is much faster compared to convection, then and then only we can apply this equation. Okay. Another dimensionless number is a Fourier number. So Fourier number compares the time for the conduction and the time required for heat storage. So that basically gives the relative time. So we will see something more on this subsequently. Okay, so this compares the relative time. All right. So up to this we have seen in the last class, and we started with this example. This example of transient heat flow in a semi-infinite solid.
Sir?
So what we are looking at in this case is there is a semi-infinite solid as shown in the figure. Initial temperature of this solid block is Ti, and suddenly this block is subjected to a higher subjected to a new temperature. Let's say it's a lower temperature T naught. So only one side of this block is subjected to another temperature T naught. This is, we have considered this T naught to be lower, but you can consider higher. Any new temperature, I am saying. Is it clear to everyone? Hello? Is this geometry is clear to everyone? Am I audible?
Yes, sir. Yes.
So we are saying that this block of infinite width x. Remember, here we are taking the width of this block as infinite. So x is starting from 0 and tending to the x equals to infinite. So this is the infinite width block. This block is initially at the temperature of Ti. Suddenly one side of this block we are subjected to another temperature T naught. Okay, and then we are looking at how my temperature is going to vary, isn't it? Now in this case, we are looking at only the heat transfer in one direction, only in the x direction. So this is what the equation we have to start with, isn't it? This is the generalized equation which we have obtained for the flat slab, isn't it? This is the generalized equation which we have obtained. Now this equation we can simplify for a one-dimensional heat transfer. So for a one-dimensional heat transfer, we will have 1 by alpha dou T by dou T dou square T by dou x square if the generation term is absent, isn't it? So that's what we are getting it here, isn't it? So dou square T by dou x square is equals to 1 by alpha dou T by dou T, isn't it? This is the equation which we have to start with. So we have simplified the original generalized equation for a one-dimensional heat transfer and without the heat generation term. Is it clear how this equation number 1 came? Is it clear to everyone? Hello?
Yes, sir. Yes, sir.
Now in this equation, again, remember in the last class I said that in such cases where the one of the dimension is becoming infinite, you will not be able to solve this equation. Why? Because at what length your temperature profile becomes Ti, this particular length you will not be able to find out. So this x equals to infinity, I can take that x equals to infinity here also, isn't it? In between, when my temperature T becomes Ti, isn't it? So that length is infinite in terms of this heat transfer, isn't it? Because my conduction is becoming 0 at this point here, isn't it? So still that length can be infinite. So what length I should take as a infinite is a difficult to obtain in such cases, correct? So this is what happens even in the Couette flow. So in such cases, solving the differential equation is possible only if you non-dimensionalize this differential equation. Okay, otherwise you will not be able to solve it. Can you see the point why we are non-dimensionalizing this equation? Isn't it this particularly this length you have to non-dimensionalize? Is it clear to everyone what I'm saying?
Yes,
hello? Because we will not be able to ascertain where this x should be infinite here, anywhere, isn't it? So x is infinite at the length where my T becomes Ti, isn't it? So some uncertainty is there with respect to that, isn't it? So in all such cases, you non-dimensionalize your length. That is what you do even in Couette flow. If you remember your transport phenomena classes, there also you might have non-dimensionalize the length. Okay. All right. So in order to solve this equation, we have to non-dimensionalize this x. Also, we have put here, this temperature we have represented by another variable theta, and this theta is given as T minus T naught, just for a simplicity, so that we can able to solve this equation easily. So T minus T naught we have put as a theta, where T is the temperature at any time T. Okay, correct. So any time T at any location x. Okay, so this T will be varying with respect to x and T both, correct? All right. So now if we replace this T here by theta, what we are going to get is dou square theta by dou x square equals to 1 by alpha dou square theta by dou T. That we can get directly because T naught is a constant term. So if we differentiate it with this, you are going to get the same thing, correct? Is it correct? Is it clear to everyone how equation 2 is obtained?
Yes, sir.
Because this T naught is constant, so if you differentiate it, this dou square T and dou T, both these things we can replace by dou square theta and dou theta. That's it, without any problem. Now, what are the boundary conditions? What are the boundary conditions? So at time T equals to 0, what will happen is this temperature profile is not developed. We will have this temperature as Ti here. Here there will be T naught, isn't it? So at x equals to at all x, at any x, but time equals to 0, there will be temperature difference, Ti minus T naught, isn't it? This will be the temperature difference, correct? Ti minus T naught equals to just theta I. Isn't it? Because Ti will be just T will be just Ti, isn't it? For all x at time t equals to 0. Do you all agree?
Yes, sir.
At time t equals to 0, this entire slab will be at Ti, isn't it? And therefore at any x, if we calculate this theta, this T will be just Ti. So that means we will have theta equals to theta I. Does it make sense? This first boundary condition to everyone? Hello?
Yes, sir.
Any students are there? 67. So we are still having how many? Just 75 or something, is it? 9 plus 67. So 76 students. Okay. All right. Sorry. Now let's look at the second boundary condition. Now second boundary condition is at x equals to 0. At x equals to 0. For any time t, at any time t at x equals to 0, this temperature will be, this temperature at the surface here will be only T naught, isn't it? So this T will become T naught. So T naught minus T naught becomes 0. So at x equals to 0, for any time t greater than 0, we will have theta equals to 0, isn't it? Do you agree with the second boundary condition?
Yes, sir.
Now let's look at the third boundary condition. Third boundary condition looks at that at x equals to infinity, at x equals to infinity, for all time t, for any time t, my theta becomes theta I minus theta naught. Because my temperature T at x equals to infinity will always be Ti. My temperature T will be always Ti at infinite length, infinite width, isn't it? So this becomes theta I. Yes or no?
Yes, sir.
Yes, sir. Yes, sir.
Now here you can see these first two boundary conditions are easy to apply because these initial boundary conditions. But this is this x equals to infinity. This is this particular boundary condition. Applying this particular boundary condition is extremely difficult because what will be the value of x equals to infinity? What value you are going to take? It's difficult to apply, isn't it? So can we get rid of this particular boundary condition by doing some mathematical analysis? So for that we require to non-dimensionalize this variable x and t. Okay, so let us non-dimensionalize this x by using another dummy variable. Let's say this another dummy variable eta we have taken. So this eta is given as x by 2 under root alpha t. So now alpha is what? Thermal diffusivity. What will be the unit of thermal diffusivity? Meter square by second, isn't it? So meter square by second into time. So time will have a unit of second. So that second get cancelled out. Alpha t will have the unit of meter square. So under root of that will be just meter, and that meter will get cancelled out with the unit of x. So this entire thing x divided by 2 under root alpha t is going to give you a dimensionless number. Do you all agree?
Yes, sir.
Again, in this case, why this specific form? Because this specific form is going to simplify your analysis. That is why this specific form we have selected. Okay, specific. You may ask that why we are using this 1 by 2 here, isn't it? So by having this 1 by 2 here, we are simplifying the analysis later. If you don't use this 2 here, you will have a factor of 2 somewhere in the final equation. Is it all right to everyone? Hello?
Yes, sir.
Okay.
Sir.
Sir, would there be another way to non-dimensionalize it without using alpha thermal conductivity?
Not clear what you are saying.
So we are non-dimensionalizing it, right? So is there a way to non-dimensionalize without using alpha in this case?
Okay, without alpha can we non-dimensionalize it? That's what you are saying?
Yes, sir.
Okay, so there is some basis for why we are using alpha. Okay, so why why alpha is used to non-dimensionalize is because see, when at what length my temperature is going to become Ti, that depends on what? That depends on the thermal diffusivity. Do you agree?
Yes, sir.
Isn't it? See, at what length my T temperature T is going to become Ti, that becomes on the thermal diffusivity. It is in a literal meaning. Thermal diffusivity is how my heat energy is going to diffuse through this solid. That is what it is.
Yes, sir.
So at what length my temperature T is going to become Ti, that heavily depends on this alpha. That's why we have used this alpha to non-dimensionalize. Can you see the point? And
Yes, sir.
isn't it? It's not arbitrarily used. It is not arbitrarily used. There is some basis for using alpha. Does that answer your question?
Yes.
Okay, all right. In fact, if you look at that cuvette flow, there you probably are using the momentum diffusivity to non-dimensionalize. Okay, in a cuvette flow, in a mass transfer, you will be using a diffusivity to non-dimensionalize. Okay. So this type of examples you will see not only for the heat transfer, but also for momentum transfer and for mass transfer. Is it clear to everyone?
Yes, sir.
Okay, all right. So with this, another dummy variable eta, now I can represent this equation to, I can differentiate this eta and then I can rearrange, I can put it in this equation, isn't it? I can differentiate this eta with respect to x and with respect to t, and then you can put it in this equation. What we will get is this equation number 3. Okay, so equation number 3 is, after differentiating eta with respect to x, you will get some equation. Also, you differentiate this eta with respect to t, you will get some equation. Then you replace this dou x square and dou t here. What you are going to get is this. Equation number 3, dou square theta by dou eta square plus 2 eta dou theta by dou n equals to dou eta equals to 0. This is what you are going to get. Do you all agree with me so far?
Yes, sir.
Now let us see how these 3 boundary conditions are going to change with this substitution. Okay, so now at theta equals to theta I, my eta becomes infinity, isn't it? So here you can see when I am getting theta I am getting theta I for time t equals to 0 and at x equals to infinity. Both you can put it here, isn't it? If you put time t equals to 0, you get eta equals to infinity. If you put x equals to infinity, still you get the eta equals to infinity. That means what? At theta equals to theta I, your eta is infinity. Or rather, I should say, when eta tends to infinity, we get theta equals to theta I. Do you all agree?
Yes, sir.
Isn't it? So both these boundary conditions are now coupled in one boundary condition here. Does it make sense? And the second boundary condition is at theta equals to 0, my eta, or I should say eta equals to 0, my theta equals to 0, isn't it? That's what it is going to be. Correct? For all t. So both these boundary conditions are clear to everyone. These 3 boundary conditions are now then changed to only 2 boundary conditions after substituting another dummy variable eta. Does it make sense to everyone?
Yes, sir.
Okay. Now let's integrate this equation. So this
Excuse
is
me, sir.
Please go ahead.
Sir, can you please explain that as theta tends to theta I, how is eta tending to theta infinity?
So see, at theta equals to theta I, look at it, this boundary condition. When theta equals to theta I, what is the value of t?
0.
If you put that value of t here 0, what you are going to get?
Sir, x is also tending to infinity as theta tends to theta I, and as theta tends to theta I, t is tending to 0.
No. So see, that second condition we will come to. First, look at the first condition. Okay. Let's look at each condition individually. So when theta equals to theta I, your time t equals to 0, isn't it? If you put that here, you get eta equals to infinity. Let's look at the another condition also. When you get theta equals to theta at x equals to infinity. So if you put that x equals to infinity here, then also you get eta equals to infinity.
Yes, sir, got it.
Okay, so for both these conditions, basically you get eta equals to infinity. So that's why you are saying that at eta tends to infinity, your theta is theta I. Make sense?
Yes.
Okay, so let's solve this equation is a standard differential equation. You can get this solution of this like this. So we can integrate this equation, and after integration the solution obtained is this. So after first integration we get dou theta by dou n is given as c1 exponential of minus eta square. Further, if you integrate this, you get theta equals to c2 plus c1 integral of exponential of minus eta square into d eta, sorry, exponential of minus eta square d eta. Now, why we have kept this second part in the integral? Because the exact analytical solution of this integral is not possible. Okay. Hello, is it clear to everyone? The second part we have kept it in the integral sign because exact integral of this is not possible. Okay, and therefore this particular integral part is represented using a error function, and this solution of this error function is given in terms of numerical solution. Okay, so I will explain this little bit in more detail. Just wait. So the solution is this: theta is given as c2 plus c1 integral of exponential of minus eta square dn. Remember, in this case, what will be the limit? Limit will be 0 to eta, isn't it? 0 to eta. And what is the value of eta? That we don't know. Therefore, this integral will not be able to solve this integral analytically. Okay. Correct? Is it clear to everyone?
So is this in some way the form which we left at non-dimensionalizing it? Like at non-dimensionalizing, we were not able to define x at infinity. Over here also, maybe because of doing that, we are able
So
to
here,
get it.
yes, that's what I'm saying. See here, this limit, upper limit here will be eta, isn't it? And that eta we don't know. Eta we don't know, isn't it? So this integral, calculating the value of this integral is not easy. All right. Okay, so therefore this integral part is represented using another function called as error function. How we have defined the error function? Error function with respect to this variable eta is given as 2 divided by under root pi integral 0 to x by 2 under root alpha t e raised to the power minus eta square d eta. Okay, so we are just multiplying this 2 by under root pi to this particular equation, and that is nothing but the error function. So if I put c1 into error function, then what I have to do? I have to multiply under root pi by 2, isn't it? Do you all agree? So that is what we are going to get. Theta will be given as c2 plus c1 under root pi by 2 error function eta. And now this value of this error function eta is calculated numerically. So this value of error function for any variable z is given in a tabulated form here. Okay, so you first calculate eta, and for the given value of eta, what is the numerical value of error function, that is tabulated here. So this error function varies between 0 to 1. 0 to 1. Okay. Is it clear? So you calculate the value of eta, isn't it? If that value matching directly with the given values here in this table, then you directly use the error function. But if it is in between any of these two values, then you do the linear interpolation and find out the error function value. Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay, so the solution of this equation is given as theta equals to c2 plus c1 under root pi by 2 error function eta, isn't it? And first you calculate the eta, calculate the value of in this error function using this table, then you put it in this equation and calculate the theta. But let's simplify this further. So here there are two constants c1 and c2. So let's apply the boundary conditions. So what was the boundary conditions? At theta, so our boundary conditions were at theta equals to tends to 0, my eta tends to 0, isn't it? So theta tends to 0, my eta tends to 0. So eta tends to 0. So that means if I put this eta tends to 0, what is the value of error function? 0, isn't it? Can you see here? So that means this entire factor becomes 0. That means C2 will be equals to 0. Do you all agree? Do you all agree?
Yes, sir.
And the second boundary condition at theta tends to theta I, when eta tends to infinity, if I am having a large value of eta, I will have the value of error function just equals to 1, because that is the limiting value, isn't it? The limiting value of my error function is 0 and 1. For lower limit it is 0, and for a upper limit it is 1, isn't it? For any infinite value of z, I will have error function of z as just 1, isn't it? So my second boundary condition also, gives me this will be theta equals to theta I. C2 is already 0, isn't it? This error function becomes just 1. So I can calculate C1. C1 is given as 2 theta I divided by under root pi, isn't it? This is what I'm going to get. Do you all agree? Hello?
Yes, sir.
So with these two boundary condition, my this final equation gets simplified. So I get theta equals to theta I error function eta. This is what the final equation we are going to get. Remember now why we have used this eta like this, x by 2 under root alpha t, because that gives me the final solution like theta equals to theta I error function eta. So this simplified form we get based on that particular condition. But if you use a different form there, some changes you will have here, but then your error function definition also has to be changed, isn't it? All right.
So how have we limited our error function to 0 and 1?
So these are calculated numerically. That is what I said. Remember, I said this equation we will not be able to calculate analytically, but numerically. That is why I have given this table. All right.
Okay, so it is just that for this example, we
No.
got that
Error function is a commonly used function everywhere. It's not only in heat transfer. You will see that use of this function, error function, in so many applications, be it a physics or in some other wide range of application. In fact, this error function you will see later on in radiation also. Okay, so error function is in a way is a standard function used in mathematics, and its value are numerically calculated like this. So that's why we have represented this entire thing in terms of error function, because error function is regularly used in mathematics. All right.
Sir, and for a very high value error being limited to 1, is that common in all error functions, or we made it or like the values came in such a way that we used?
No, this numerical value comes nearly close to 1. So if you increase this z function further, you will get it 1. Okay. So I am not sure whether we have the derivation of this later on. Maybe this derivation we probably have later on in radiation somewhere. Why it should be 1 or something. Okay, I'm not able to recall it, but mathematically, by solving this numerically, you will get the upper limit equals to 1. Okay. All right.
So by solving numerically also there would be some error in those numerical analysis. So
yes. But see, we will have some error. You are absolutely correct. But if you do it for smaller step size, you can get it fairly accurate. Okay. All right.
So we are getting 1 because is it a normalized Gaussian integral?
You are saying that because it is a Gaussian integral, that's why we are getting the upper limit equals to 1 and the lower limit equals to 0. That's what you are saying?
No, sir. The infinite error function of that one.
Just a minute. Hello.
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 Hello. Am I audible?
Yes, please go ahead.
So I was telling because this is a normalized Gaussian
No, see,
integral, so
only problem with this integral here is this limit itself is, you will not be able to find out the exact value of this upper limit. What will be the upper limit? X by 2 under root alpha t. What is x here? X is the, in this case, you are going to use this x, which is nothing but the length at x equals to infinity. Isn't it?
Yes,
and what
sir.
is that x equals to infinity? That depends on, see, here we are putting x equals to infinity, but in actual sense, it's not infinity. It will be some value. Isn't it? We wanted to calculate at what value my my temperature T is going to become Ti. That characteristic length we are interested in. And that characteristic length is the infinite length. Isn't it? That's why it is, difficult to, calculate the value of this integral, and therefore we are using the, numerical method, so that, see, in this case, this z we have not used infinite. Can you see?
Yes,
in this
sir.
table, you can see this z is not infinite. It is some finite value, but this, even this value of 3 is equals to infinite in terms of this equation, in terms of this situation, isn't it? For this problem, z equals to 3 or this x equal, this eta equals to 3 still becomes infinite in this case. Isn't it? Can you see the point? I am saying that this integral is not able to, we are not able to calculate only because this upper limit is uncertain. This upper limit is uncertain. That's why we are calculating the value of this error function numerically for all the values of z, with the z increasing. This z is nothing but eta here, isn't it? But you will see that when z equals to 0, you get the lower limit equals to 0, and as the z increases, this curve becomes flat. Even if you increase the z value beyond this, your value is going to be just equals to 1. It's not going to vary. All right.
Sir, as far as I know about the error function, it is like this function e to the power minus eta square dn cannot be integrated, and
So
that's
that's
why
why. So see, that is why we are doing it numerical integration. That's what we are
right,
saying.
sir. Sir,
That's what
and
we are
the
saying.
error function is something which gives us some kind of probability. I don't know it fully yet, but that probability is 0 to 1.
Sorry. I understood. I think don't get confused with this name error. Okay. I think some people might be getting confused with this name error. It's not about that. But whatever our friend is saying, this is some kind of probabilities. Yes. But the same equation you will be using later on also in the radiation. So very often you get such situation where, finding this integral is not easy, isn't it? And therefore you calculate it in terms of a standard function like this error function, and the numerical values of this error function with respect to this z are already known. People have calculated it, and these are tabulated. So that's why this table I have given here. Okay. Don't get confused with this name error. It's not error. Okay. Even though we are calling it as a error function, but this is basically given this name to this entire integral. Okay. It's not the error or anything. All right.
Yes.
Okay. All right. So this is the final equation which we have obtained. This is theta equals to theta I error function eta. And what we are saying is how we can solve this equation or get the values. We first calculate eta. Eta we can calculate using this equation. X divided by 2 under root alpha t. We can calculate the eta because in general the questions is asked as at what x value the x value is given, isn't it? The width is given, and then the question is what will be the temperature at that particular x. So this x value is known, isn't it? So for the given value of x, we can calculate the eta, check that eta value here and calculate and find out the corresponding value of error function. Sometimes you will see that your eta is exactly matching with this values given here. Then you don't have to worry. Otherwise, if it is in between two values, then you do the linear interpolation. and find out the error function value, and then that error function value you put it here. Theta I is nothing but what? Theta I is nothing but this T minus T naught, Ti minus T naught, isn't it? Correct. So this is what nothing but the theta I will be this Ti minus T naught, isn't it? So T minus theta I is nothing but this theta minus, so theta is going to be T minus T naught, that is theta, and divided by theta I is nothing but Ti minus T naught, isn't it? So that's what we are going to get. Theta divided by theta I equals to error function of eta. That is what we have written here. Theta minus theta I is given as error function eta. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
Okay, so let's further extend this analysis for some calculations. So remember, in this case, eta is a dummy variable, and very often we are interested in finding out the heat flux or the rate of heat flow, isn't it? That's what we are interested in. Very often we are interested in finding out what will be the rate of heat flow here or somewhere in between here, isn't it? Correct. So whenever we are interested in finding out rate of heat flow, what we are interested in finding? We first find out the heat flux at that location, and that heat flux, when we multiply that heat flux by area, then we get the Q at that particular location, isn't it? Correct. So in this case also, since the solution we have obtained, this entire solution we have obtained in terms of eta, and eta is a dummy variable, we wanted to find out the solution in terms of the known quantities like Q or small q, etc. Isn't it? So for that, let us integrate this equation number 4. This is the equation number 4, where C2 is 0 and C1 is given as 2 theta I by pi. I can integrate this equation with respect to x, isn't it? Because dou t by dou x is what we are interested in calculating. Flux will be what? Minus k dou t by dou x, isn't it? So first we are calculating dou t by dou x. So dou t by dou x we can directly calculate from this equation. In this equation, in equation number 4, this C2 is 0 and C1 will be just this 2 theta I by pi. And what is theta I? Theta I is nothing but Ti minus T naught. Whereas theta is what? T minus T naught. I can differentiate this equation with respect to x, isn't it? And after differentiating this equation with respect to x, we can find out dou t by dou x. So that's what we have done. So after integrating this equation, what we get is, remember, left hand side will be t minus t naught. So t naught is a constant. So dou t by dou x will be, directly you can get dou t by dou x, isn't it? Because dou t naught by dou x is 0, isn't it? Right hand side, theta I term is there. So theta I term is what? Ti minus t naught. So Ti minus t naught term we have taken out as it is. And differentiation of this term in the integral which we have done. Now eta we have replaced by actual variables, this, isn't it? Actual variable, this x by 2 under root alpha t. If you differentiate this term in the integral, what we get is this. Ti minus t naught 2 by pi. This is already from theta I. This is already from this 2 theta I by pi, isn't it? So that is what is directly written here. And then differentiation of this integral term, that gives exponential of minus x square by 4 alpha t dou by dou x, x by 2 under root alpha t. If you rearrange this entire term, what we get is Ti minus t naught under root pi alpha t exponential of minus x square by 4 alpha t. So what we have done, again I am repeating. First we have put C2 here is 0. Then we have put C1. C1 is nothing but 2 theta I by under root pi. So what is theta I? Theta I is nothing but Ti minus T naught divided by Ti minus T naught, and so this 2 theta I by pi will be basically 2 into Ti minus T naught divided by under root pi. So that we have kept as it is. See, Ti minus T naught 2 divided by under root pi, this is kept as it is because this is a constant term. And then we have differentiated this term in the integral by replacing this eta by this equation, x by 2 under root alpha t. So this differentiation of this integral gives us this exponential of minus x square by 4 alpha t plus dou by dou x divided by 2 under root alpha t. And if we rearrange this entire thing, what we get is ti minus t naught divided by under root pi alpha t exponential of minus x square by 4 alpha t. So if we rearrange this everything and multiply this by k into a minus k into a, remember this is dou t by dou x, isn't it? What will be qx? Qx will be minus k dou t by dou x. And what will be q? Capital Q. Capital Q will be area multiplied by this. So that's why q is given as minus ka ti minus t naught under root pi alpha t exponential of minus x square by 4 alpha t. Is it clear, this term, entire term, how we got it? Hello?
Sir, why have we differentiated the integral?
Because we wanted to calculate dou theta by dou x.
Okay, sir.
Isn't it? We are interested in finding dou t by dou x, na? So this theta is basically what? T minus t naught. So dou theta by dou x is same as dou t by dou x. Do you all
Yes,
agree? So that's why we are differentiating this. Is it clear? Is it clear? This part, how we got q?
Yes, sir.
Minus ka into dou t by dou x will give you q, capital Q. So this is the q value at any x. This is very important. So with this equation, now I can calculate what will be the value of heat flow at any x, isn't it? I can calculate here, anywhere using this equation. Correct. Now another interesting thing to look at, but the heat is added. See, I can calculate q here, but where the heat is added? Heat is added only on this surface, on this left hand side surface, isn't it? So total amount of heat added to this flat slab, I can calculate by calculating the heat added here at this location here and then integrating it with respect to time, isn't it? Because this is also varying with respect to time. How much? See, what will be the unit of Q? Q will be watt. Watt is what? Joule per second, isn't it? So I can calculate how much heat energy I am adding in this slab in a given time, isn't it? Do you all agree with me? Hello?
Yes, sir.
So that for that we need to calculate what will be the Q value, capital Q value here at the boundary, because that is what the amount of heat I am adding. See, no heat is added in between. Only the heat is being transferred here. Isn't it? Inside the slab, the heat is being transferred, but heat is not being added additionally. Heat is being added only at this left hand side surface. Isn't it? So I can calculate how much heat is added. Sorry. Exactly at this left hand side surface here, and then I can integrate it with respect to time, and I can find out how much total amount of heat I have added to this flat slab over the time. So for that we have calculated this Q naught at x equals to 0, that I can directly obtain here by putting x equals to 0. So this exponential term becomes 1, isn't it? This exponential term becomes 1. So we get Q naught is given as minus Ka Ti minus T naught divided by under root pi alpha t. Now this Q naught I can integrate over time to calculate the total heat added over the time, isn't it? So if I integrate Q naught dt, in this equation, this, remember, this t is variable here, so I can take everything out here, but this under root t dt by under root t will be there. So if we integrate that with respect to t0 to t, what we are going to get is 2 Ka. So this minus sign we have got rid of by changing this t naught. We have interchanged this. So this difference we have now calculated as t naught minus ti. So 2 Ka t naught minus ti divided by under root pi alpha by t. That is what is going to give us the total heat added over the time interval 0 to t. Do you all agree? Is it clear to everyone what we are doing?
Yes, sir.
Hello. Okay. So let's look at one example on this. So this Biot number we have already seen. Okay.
Sir.
Please go ahead.
Sir, how do we calculate that characteristic dimension S? I mean, is it given or?
Okay, so characteristic dimension for the sphere will be what? Radius.
Oh,
Isn't it?
okay. I thought it is some physical quantity which needs to
No.
be calculated.
So this characteristic dimension S becomes difficult to calculate when we are looking at non-regular surfaces. Non-regular surfaces like annular surface you are taking, let's say. There you have to calculate this characteristic dimension in a slightly different way. We will see that as we go ahead. But in a normal geometries like sphere or radius, this characteristic dimension will be sphere or cylinder. This will be radius. Okay. For a flat slab, it will be X. Do you agree? Or
Yes.
L, isn't it?
Yes, sir.
All right. So let's take this example of a transient heat flow in a semi-infinite solid. So calculate the temperature in plane 200 mm from the surface of a very thick wall, and also the heat flowing per unit area of this plane 10 hours after the surface temperature of the wall changes from 25 to 700 and remains constant thereafter. So initial temperature was what? So in this case, 25 was the initial temperature, and then suddenly we have changed to 700, isn't it? Correct. Also find the total heat energy taken up by the wall in 10 hours per unit area. Assume the wall material thermal conductivity is given, and this diffusivity is given, that is 0.003 meter square per hour is given. So we can calculate in per second also, isn't it? So in this case, this is the equation, isn't it? Correct. This is the equation. Now this surface temperature, this location is given, isn't it? Calculate the temperature in plane 200 mm from the surface. So X value is 200 mm, isn't it? So that is 0.2. Correct? Yes or no? Again, the time is given 10 hour. Alpha value we already know. We can calculate X by 2 under root alpha t. So that is nothing but zeta, isn't it? Eta, isn't it? This is nothing but eta. X by 2 under root alpha t is the eta. Correct? So that eta we can calculate, eta comes out to be 0.577. Now you can go back here, 0.577 is somewhere here, in between here. Sorry, 0.577, na? Just a minute. 2, somewhere here, isn't it? Do you all agree?
Yes, sir.
Yes, sir.
So between 0.5 and 0.6,
Yes, sir.
you will have 0.577, isn't it? So you can do the interpolation of these two values and calculate what is the value of error function, isn't it? So error function of 0.577 comes out to be 0.585. That's what you are going to see here. If I go 0.585, that's what is in between here, isn't it? Can you see?
Yes, sir.
So you calculate the value of this error function, isn't it? Then now put all the values here in this equation. Temperature you have to calculate, isn't it? This temperature you don't know. T naught you know, isn't it? T naught you have been given 700, isn't it? What is Ti? Ti is 25, isn't it? So T minus 700 divided by 25 minus 700, and that is equals to 0.585, isn't it? You can back calculate what will be the temperature at this location X and time, isn't it? So this comes out to be 305.12. Is it clear? Hello? Is it clear how we have calculated?
Yes.
We have used the same equation. We have just put the values of this eta, and then eta we have used to calculate error function. Error function value we have put in this equation, and then back calculated the temperature at this location, which is 200 mm from the surface at time 10 hours. So here we are directly multiplying 10 because this diffusivity is given in meter square per hour. So that get cancelled out. Okay, so it doesn't matter. All right. Hello. Is it all right? to everyone?
Yes, sir.
Yes.
Okay, now then what we are interested in finding out. So first part is clear. We have calculated this temperature. That's first part is clear. Second part is also find the total heat energy taken up by the ball in 10 hours. So we wanted to find out integral of Q naught dt over the time 0 to 10 hours, isn't it? Do you all agree? So for that,
Yes.
first we have to write this equation for Q, isn't it? So rate of heat flow. Okay. We are also interested in finding the rate of heat flow. Also the heat flowing per unit area. Okay, so this rate of heat flow Q per unit area at this location also we have calculated. So this is the same equation which we have used here. This is the same equation we have put it here. Okay, and we are putting this X and T value and calculating what will be the rate of heat flow at this location of 200 mm from the surface after 10 hours. So that comes out to be again 11.03.5 watt per meter square. This is just putting the values directly here, isn't it? Clear? Then
Yes, sir.
total heat added over the time interval 0 to 10 hours that we have obtained by doing the integration here, isn't it? So that is given as 2 Ka T naught minus Ti under root pi alpha by T. Let's put all the values here. So if we put all the values here, then we get the total amount of heat added over the 10 hours per unit area. So per unit area is there. So this area we have taken. So this comes out to be joule per meter square, isn't it? Is it clear to everyone? This thing?
Yes,
It's
sir.
the same equation except that now the unit will be joule per meter square because now we have integrated with respect to time. Correct? All right.
Yes, sir.
Okay. So let's continue with the next thing. Let us try to solve a multi-dimensional steady state conduction. So in this particular example, what we are using, a flat slab is there. In a flat slab, only two-dimensional heat transfer we are looking at. So that means in a Z direction, the temperature at any location is constant. So Z direction we are not looking at. Again, the temperature here on this particular surface is 0. At this surface is 0. Here the temperature is 0. And the temperature is only varying along the x-axis here. And that is given by T is equals to f of x, where f of x is any function. It could be linear, it could be exponential, it could be sinusoidal, any function. This wording is very important. T is given as f of x. F of x is any function. This word is very important here. Why that is important, I will come to very soon. Okay, so the problem is clear to you. There is a flat slab. Only the temperature is changing along this slab on this x-axis, and we are interested in finding out how my temperature is going to vary across this flat slab. And we are trying to solve a two-dimensional system. So that means only we are interested in looking at how my temperature profiles are going to vary across this xy plane. In a z direction, we are assuming that the temperature is same across the z direction at any location. Does it make sense?
Yes, sir.
Okay. So we are solving it for a only two-dimensional thing because we wanted to appreciate how the numerical solution or an analytical solution of this particular system will look like. That thing we are trying to appreciate. Of course, this type of systems are people generally solve using the numerical methods. In fact, this is what people solve in CFD, isn't it? In CFD, that's what they do. Correct. So whenever in computational fluid dynamics, when people are interested in finding out the temperature variation, they solve it numerically. They solve it numerically. Okay, but here we are trying to solve it analytically so that we can appreciate the solution procedure of this and how my temperature profiles are going to vary, what type of boundary conditions are will be there. If I wanted to solve this for the cases where even these other sites are also having some temperature functionality, isn't it? So that type of thing we are interested in. Why we are looking at it? Because such situations have several practical relevance. Okay, so in a real practical situation, heat conduction takes place along more than one dimension. This is specifically true if the system has irregular boundaries and or with non-uniform temperature along the boundaries. The temperature in these systems may vary in 2 or 3 coordinate directions, and multi-dimension heat conduction analysis must be made in order to understand temperature distribution or heat flow through the systems. Okay, so this type of situations we see mostly in a cases where there are different shapes of the metallic objects are there, or even composite bodies are there like chimneys or air conditioning ducts, etc. Okay, all right. A more practical relevant system I can tell you. Okay, maybe this example is what people look at nowadays. So how the heat transfer takes place inside the computer. Okay, remember, if you look at, I don't know whether you have opened your computer at any time or not, you can see that in your computer you will see there is a fan rotating backside which removes the heat which is generated inside the circuits which are there, isn't it? But if you look at these internal circuits where the heat is getting dissipated, how that heat is going to get dissipated from the different metallic parts. If you wanted to calculate that, you have to solve similar type of situations. Can you see the relevance of this? At least in terms of this, new generation application. And this is very important because the speed of your computer or speed of your transistors which are encoded inside that silicon chip, that depends on how fast you can remove the heat out of it. Can you see the point here?
Yes, sir.
Okay. So in fact, those who are looking at the fabrication of these hardware units, they're solving the heat transfer across this metallic part is very, very important. Very, very important, because if you use the geometry in such a way that your heat dissipation becomes easy, then you can improve the speed of your computer. Okay, speed of your computing. So all these questions becomes extremely relevant even today's life. Okay, all these heat transfer equation people have solved almost 50-70 years before, but these are still relevant in practical application today. All right, does it make sense to everyone what I'm trying to say?
Yes, sir.
Okay. So let us, try to solve this problem analytically. Again, I'm saying again and again that we are solving it analytically just to appreciate the concept. But in a real life situation, people solve it mostly using numerical methods. Okay. So as I said that this flat slab has the length of A and the width of, let's say, width of this B. Again, the temperature at these three sides is T equals to 0, and here the T is f of x, and this f of x is any function. It is any function. Okay, it could be linear, it could be exponential, it could be sinusoidal, isn't it? Now the boundary conditions are at x equals to 0. At x equals to 0 here, the temperature is 0. At x equals to A here, the temperature is again 0. Okay. At y equals to B here, the temperature is 0. And at y equals to 0, my temperature is T is f of x. All right. Now how we can solve this particular system? Remember flat slab, what I said. If I go back, the generalized equation we have derived. This is the generalized equation we have derived. Isn't this the generalized equation we have derived? So if I say that my accumulation is 0, if my generation term is 0, and only I'm looking at two dimension, that means this dou square t by dou z square is also not there, then I will have dou square t by dou x square plus dou square t by dou y square equals to 0. My Laplace equation gets simplified as dou square t by dou x square plus dou square t by dou y square equals to 0, isn't it? Do you all agree? Hello?
Yes, sir.
So this is what I have used here. I have used directly a Laplace equation for two-dimension heat transfer, isn't it? So I am assuming that there is no accumulation term, and also there is no generation term. Okay. So now this particular equation number one, we can solve this equation number one by using the method of variable separation. So what is method of variable separation is, in the method of variable separation, what we are doing is, since t is a function of x and y only, the solution we are assuming as t is given as xx and yy, and in this case the xx is only function of x, whereas yy is only function of y. That's why we are calling it as a variable separation. We are selecting this xx and yy such that these are function of x and y alone. So where xx is a function of x alone and y is the function of y alone, we are assuming a solution like this. We are assuming this solution like this. Okay, we will see whether this makes sense or not, isn't it? In fact, it makes sense if you select a particular form of the solution, then and then only it makes sense. Okay, so what in a physical way, what we are doing? In a physical way, what we are doing is we are calculating the solution which is function of x alone and then y alone, and we are calculating that in such a way that their multiplication is going to be the actual solution t. Okay, is it clear to everyone? This is the standard used in mathematics. Okay, so we are not inventing something new. Is it clear to everyone what we are doing here?
Sir.
Yes, sir.
Okay, so we are saying that the solution of this equation, remember the solution of this equation will be given as what? T will be function of x and y. Do you all agree? I am saying I am going to represent the solution T, which is function of x and y, in two parts. One part is a function of x alone and another part is a function of y alone. Isn't it? That's what we are doing here. So t is given as xx into yy, where xx is a function of x alone and y is a function of y alone, and that's why this methodology is called as a variable separation method. This is popular in mathematics. Okay, so now for this case, the solution, if we are assuming that xx is a function of x alone and yy is a function of y alone, we can represent this equation 1. We can represent this function 1 in terms of x and y directly, isn't it? So we will get 1 by x, 1 by capital X, d square x by dx square. Now we have omitted partial differential equation, isn't it? Because now this t we are representing by using the terms in the x terms, and this t we are representing in terms of y terms. And if we differentiate it, then what we are getting is this 1 by x d square x by dx square, and that is equals to minus 1 by y d square y by dy square. Do you all agree? If I put this t in this equation and differentiate it, this is what I'm going to get it. Do you all agree? Hello? Hello?
Yes, sir.
Yes, sir.
Now, here left hand side and right hand side. Remember here we said x is a function of x alone and y is a function of y alone, isn't it? That means what? Right hand side and left hand side should be equals to a constant value. Do you all agree? Isn't it? If it is not a constant value and if it is a function of any other y or x, then it is not independent, isn't it? Then we will not be able to say that this is a independent of x or independent of This part is independent of y. So this equation number 3 can be true only if both left hand side and right hand side is equals to a constant value. Do you all agree?
Yes, sir.
Yes, sir.
Yes, sir.
So okay. So that is what we are saying. Okay. Okay. All right. Just a minute. So what we are saying here is this 1 by x d square x by dx square, this part will be independent of this right hand side, and right hand side will be independent of this. So these are represented, since each side of the equation is independent of the other, x and y being the independent, it follows that each side may be equal to a constant. Okay, equals to a constant. So if we put that constant here as a lambda square, why we are taking it as a square? Why it should be a plus lambda square? Whether it should be minus lambda square? This is governed by the boundary conditions. This is governed by the boundary conditions. Okay. So in this case, we are going to use this as minus lambda square. This 1 by x d square x by dx square will be equals to minus lambda square. Okay. So if we use that minus lambda square, then all the boundary conditions are going to satisfy. Why I am saying this? Okay. Let us look at each of these, things little bit in more detail. So if I assume that 1 by x d square x by dx square equals to 0, and that is equals to 1 by y minus 1 by y d square y by dy square. If we assume that both this right hand side and left hand side is equals to 0, remember any constant means it can be 0 also, isn't it? But if you put the 0, you will see that you will get this x and y as a linear functions. And if these are linear functions, remember this t is any function. It could be a sinusoidal wave, it could be cosine wave, it could be any function. So this particular boundary condition will be violated if I use this constant to be 0 here. Okay. And same argument is true if we use the positive lambda square here. If I use a positive lambda square, you will see that the temperature values which are obtained comes out to be only exponential here. Only exponential temperature profiles can be satisfied. But this t can be exponential, it can be linear, it can be even sinusoidal, isn't it? So that means we require a function which is giving me a sinusoidal wave here, because sinusoidal waves can satisfy linear, it can satisfy sinusoidal, it can satisfy even exponential, isn't it? That is the reason why Fourier transform is usually used for representing any curve. Do you all agree? Yes or no? Can you see the point?
Yes, sir.
I am kind of asking you a new probably why Fourier transform is used for signal processing. A general question I am asking. Why Fourier transform is used for signal processing, or Fourier series is used for signal processing? Because Fourier series gives you a combination of sine and cosine waves, and sine and cosine waves combination of that can represent any function, be it a linear, be it a cosine sine, be it a exponential. Any function can be, or any type of curved lines can be represented by Fourier series. And that is the reason why Fourier series or Fourier transform used in a signal processing. Same argument I am giving here. My argument here is, if I get my temperature profile here as exponential, it is not going to satisfy my sine or cosine wave here. If my function is, let's say, sine wave, isn't it? So that means all type of temperature profile I will not be able to satisfy if I get my temperature profile as exponential or linear. The only way I can satisfy that is if I get my temperature profile here as sine or cosine waves. That's it. And that you can get only by using the constant value here as plus lambda square. Sorry, minus lambda square. That minus sign is important. If I use plus lambda square, I will get exponential waves. Do you all agree now? Hello?
Yes.
You can see, as I said, argument is like this. If I can start with a zero value, I can solve, and then I can look at this boundary condition. Then I can look at all these boundary condition. If any of these boundary conditions are violated, that means selected constant value is not correct. Similarly, if I start with plus lambda square here, then also the boundary conditions will be violated. The boundary conditions will be satisfied only if I use this right hand side, this right hand side here as minus lambda square. Only a negative value of the constant, say lambda square, will satisfy all the prescribed values of the boundary condition, because it will give a Fourier series expansion of f of x in terms of sine and cosine functions. Is it clear to you what I'm saying?
Yes, sir.
Okay, so this is slightly more philosophical. Okay, unless you try to try to bring that knowledge from your mathematics to understand why specific form is used, otherwise it becomes all equations. But there is much more than equations. Okay, much more than equations is why we are using minus lambda square, because it is only that value is going to give me sine and cosine function, and only the sine and cosine function can satisfy all the conditions, be it a linear, be it a constant, be it a sinusoidal wave, be it any exponential wave. All this type of requirement can be satisfied only by sine and cosine wave. That is the reason why in signal processing, to represent any curve, we use the Fourier series. That is what the rationale behind the Fourier series or Fourier transform is. The same concept is used here. Okay, I can get the solution which is satisfying any boundary condition like t equals to any general function f of x. That is possible only if I get this sinusoidal or a cosine wave here for temperature. Okay, so with this, all right, so it is already 10:55. So we will stop here. We will continue from this point onward in the next class. Is it clear to everyone what we are trying to say? Hello? Is it clear to everyone? We will continue. In fact, I wanted to complete this part today, but anyway, we will continue in the next class.
Excuse me, sir.
Please go ahead.
Sir, can you please explain this part once again, that how to choose the constant lambda square?
Okay. So I have already given some more information here. Okay. Okay. Let me just make it big. So what we are trying to say here is, with this equation, we are going to, what we said, that this equation is true only if my 1 by x d square x by dou x square is equals to some constant, and similarly minus 1 by y d square y by dy square is equals to some constant, isn't it? Then and then only this equation is true, because both left hand side and right hand side are independent of each other. Do you agree with this? Up to this,
yes,
do you agree? Okay.
Yes.
Now, then once we said that both these terms will be equals to some constant. Now the question is what constant I should select. Now when I'm saying both the sides are equals to constant, that means I can take even 0, isn't it? Correct? Do you agree with me?
Yes.
But if I take a 0, that means this right hand side and both left hand side is equals to 0. What this solution is going to give me? Remember, this is d square x by dou x square will be equals to 0. And what will be the solution of that?
A linear function.
C1x plus C2, isn't it? Similarly, we will get y1x, y1 C1 plus C2, isn't it? That is what you are going to get the solution, correct?
Yes.
But when I am saying t is equals to f of x here, whether this linear form of the solution is going to satisfy this boundary condition? Because this f of x is any function, I am saying, any function. It could be any function. I am not saying whether this t equals to f of x is a linear function or not. I am saying it is any function. Are we going to satisfy that? It's not, isn't it? Because this solution, now you are getting a linear function. It will have a specific form. It will not satisfy any general form like t equals to f of x. Do you agree?
Yes.
And same argument is true if I use this constant as a lambda square. If I use a lambda square here, the temperature profile here I am going to get exponential. You will get the exponential terms. Now that exponential term also will not be able to satisfy any general form of a function t equals to f of x. So only way this equation is going to satisfy my all boundary condition is if I get my temperature profile in terms of sine and cosine, and that I can get only if I use minus lambda square as a constant here. Do you agree? That
Yes,
square
sir.
is
Yes,
only
sir.
for
Got
the
it.
mathematical manipulation. You can use minus lambda. That's it. Minus lambda or plus lambda. Plus lambda will give you exponential term. Minus lambda will give you sine and cosine terms. So sine and cosine terms are going to satisfy any function because sine and cosine can satisfy constant, can satisfy linear, can satisfy any general form of function. That is the rationale behind using this sine and cosine function in Fourier series. So same argument we are using here. Unless I get my temperature profile in terms of sine and cosine, I am not going to satisfy such boundary condition where my t is given as any function f of x. Do you agree?
Yes, sir. Yes, sir. Got it.
So that's why we are using this specific form of minus lambda square. But instead of t equals to f of x, let's say this particular boundary would have been 0. But this y boundary is, let's say t equals to f of y would have been there, let's say here. So when x boundary is there, then we use minus lambda square. But when y boundary is any function, then we use plus lambda square. This is the difference. Okay. When this y boundary is plus lambda, because see here this minus sign here is with y, remember. So whenever our y boundary is any function, in that case we use plus lambda square. Do you agree now?
Yes.
And can you see why we are using plus when y boundary is any function, and why minus sign is used when x boundary is any function? Because minus sign is associated with this y. There is no minus sign associated with this x. Therefore, whenever we are solving for x boundary like this, then we use minus lambda square. But when we are having this, let's say we are having this t equals to f of y here on the right hand side here, then we will be having, and this all other faces are 0. In that case, we would have used plus lambda square. Do you all agree? Because this minus sign will be directly from there.
So, but if you
Yes.
multiply minus on both the sides, then it would come on the side.
So see here we will get a function of here in this case all this y are 0. You will get a temperature of in terms of x. Okay, and that will be given in terms of sine wave, sine and cosine wave. But if this f of y is there, in that case you will get a function of sine and cosine wave of y. All right. So we will see the entire solution. We have not even started with the solution. We will get the entire solution later. Okay. All right. Hello.
Yes,
Can we
sir.
stop? Can we stop here, or is there any question?
Can we start at this lambda? How are you using lambda next time also? Like, can you start from that one?
So see, we have solved only for one case, but you can solve it for the another case also in a similar manner. And why that is required is also important question, because see, it's not that only one surface is going to have a temperature variation and other surface will not have any temperature variation. It's not going to happen. So in fact, how analytically it is solved, we solve it for one surface each, and all these contributions then we add. That is what we do in a Fourier series also. Remember, because you get the solution in terms of sine and cosine wave, and these are additive. These are additive, isn't it? Do you see
Yes,
the point? Isn't it?
yes.
So we get the temperature profile with by including only a x surface first, then y surface, and then we add so that we can get the combined effect. That is what we are going to see towards the end of this particular topic.
Okay,
All
so,
right.
so but over here, when like the only point where I had it out of lambda was like when you told that it's because y is attributed with the negative sign in the from one.
So see, this negative sign is going to see.
If you
If I
multiply
use,
-1 in third equation, then we'll get negative sign to x side, right? Then how does lambda choosing lambda depend on that?
okay,
Should we?
I
My doubt is basically, should we know the?
I understood your question. You are saying that we can take this negative sign here,
Yes.
isn't it? On the left hand side, isn't it?
Yes, sir.
Correct. Then we have to use plus lambda square here.
Yes, so basically we in a way know what we are going to do. That's why.
Yes. So see, ultimately what we are doing is what equation, individual equation we are selecting. That important. If I'm using this 1 by x d square x by dx square, then I will use lambda square minus lambda square. Otherwise, if I'm using minus sign here, then I will use plus lambda square, so that I can get this specific forms, equation 4. Can you see?
Yes, sir. Yes.
So this is perfectly all right. Whatever you said is correct. Okay, so let us stop here. We will continue from this point. This is slightly more
So sir,
complicated.
we just have we just want that the function of the t is a function of x. So we want the sine and cosine to be in the x direction.
Yes,
So that's
direction.
why we are choosing it like this. And if it would have been a function of y, then we want a sine and cos to be in y direction. That's so we will choose positive lambda square. Is that the reason?
Precisely. Yes.
Okay, sir.
Yes,
So we
precisely.
are choosing it on the basis of the temperature function.
Yes, and we are saying only sine and cosine can satisfy any general boundary condition.
Yes.
That is why that specific form is required. If you don't use that specific form, it may satisfy. Let's say if we use the lambda square and my temperature is also varying exponentially, it may satisfy some specific form, but not a general form. General form can be satisfied only by sine and cosine waves.
Yes.
Make sense?
Yes.
Okay, so let us stop here and we will continue with this